So if you we break down the components of the singular value decomposition. We can take look at the u's, the kind of the u and the v matrix, so the left singular values and the right singular values. So you can if you look at the original data matrix here on the left, so that's the image plot here that we saw before. And then on the in the middle plot here, I plot the first left singular vector, and it kind of roughly shows basically the mean of all of that kind of data set. So if you plot it across the rows, you can see that the first singular vector is kind of has a negative value for rows kind of 40 through about 18 or so, or 17, and then has a positive value for the remaining rows. So that shows the clear separation in the means of the two sets of rows, right? And if you look at the first right singular vector, you can see that this also shows the change in the mean between the first 5 columns and the second 5 columns. And so the nice thing about the singular value decomposition here is that it immediately picked up on the shift in the means, both kind of in the row, from the row dimension and the column dimension, without you having to tell it anything. It was totally unsupervised, and it just kind of picked it up automatically. So remember, we made a plot that was very, very similar to this before, but that was when we knew that there was this kind of pattern in the data set. So here, the singular value decomposition picked up the pattern right away, and in the first kind of singular left and right singular vectors. Another kind of component of the singular value decomposition is known as the variance explained. And this comes from the singular values that are in the D matrix. So remember, the D matrix is really a diagonal matrix. So it only has elements that are on the diagonal of that matrix. And you can think of each singular value as representing the percent of the total variation in your data set that's explained by that particular component. And the components are typically ordered so that the first one explains the most variation as possible, and the second one explains the second most, etc. And so you can plot the kind of proportion of variance explained as we have in this plot below. And so here on the left-hand side, I've just plotted the raw singular values, and you can see that they kind of decrease in value as you go across the columns. But of course, the raw singular value doesn't really have much meaning because it's not on an interpretable scale. So if I divide by the total sum of all the singular values, then on the right-hand side, I can interpret it as the proportion of variance explained. And you can see that it's exactly the same plot, but the y-axis has changed. And so you can see that the first singular value, if you recall, it captures kind of the shift in the mean in between the rows and the columns. That captures about 40% of the variation in your data, right? So almost half of the variation in the data is explained by a single kind of singular value, or you can think of it as a single dimension. And then the remaining variation in the data is explained by the other components. So just to show that the relationship between the singular value decomposition and the principal components is close, I've calculated the SVD and the PCA of the same data matrix, and I plotted the principal components on the x-axis and the first principal component on the x-axis, and the first right singular vector on the y-axis, and you can see that they fall exactly in a line. They're exactly the same things. So the SVD and the principal components analysis is essentially the same thing. And so if you hear, if you're in a cocktail party and you hear two people talking about the SVD and PCA, you can rest assured that they're basically doing the same thing. So take a closer look at the variance explained. Here I've got a very simple example, which is just basically kind of a matrix that has either zeros or ones. And so the idea is that there's only one pattern in this matrix, right? And so the first 5 columns are zeros, and the second 5 columns are ones. That's it, nothing special. And so if I plot the data, you can see that on the left-hand side, the left plot, the first 5 are red, and the second 5 are yellowish white. So now if I take the SVD of this kind of relatively boring matrix, you can see that I can plot the singular values, and you can see that there's one singular value that's very high, and the rest are all kind of zero, basically. And what you'll see is that the first singular value explains 100% of the variation in the data set. So how can that be? Well, if you think about this data set, even though there's kind of 40 rows and 10 columns, there's really only one dimension to this data set, which is that if you're in the first 5 columns, you're equal to 0, and if you're in the second 5 columns, you're equal to 1. So even though you have lots of so-called observations, there's really only kind of a small fraction of information that's actually useful in this matrix. And so that's captured by the SVD by the fact that you can explain 100% of the variation with a single component. So let's add a second pattern to the data set. So we can add a pattern that kind of goes across the rows, and it also goes across the columns. And so the first pattern is going to be kind of a block pattern that we saw before. So the first kind of half the data set is going to have one mean, and half the data set is going to have another mean. And the second pattern basically is going to alternate between the columns. So you can see what that looks like over here. So on the left-hand side, that's the data, and you can see that there's one pattern that's kind of a block pattern. So the left 5 columns are low, and the right 5 columns are higher. And then you can see that within that, kind of nested within that, is a kind of pattern that's kind of every other column. And so the every other column one is higher than the other. And so if we plot the kind of what the truth is, right, we can see that in the middle plot here, the first 5 columns have a lower mean, and the second 5 columns have a higher mean. And that's the first pattern. And then the second pattern shows that the first column has a mean of 0. The second column has a mean of 1. The third column has a mean of 0, and the fourth column, etc. So there's 2 patterns here. One is this shift pattern, and the second is this kind of alternating pattern. So that's the truth. But of course we rarely know the truth, and so we need to learn the truth from the data. So the idea is that if you were presented with the data set that we've shown here on the left, can you come up with an algorithm that can pick up on the 2 separate patterns that are buried within the data? And so that's kind of what the SVD is for. So if we run the SVD on this new matrix with the 2 patterns, I got the data here on the left. In the middle panel here, I've got the first right singular vector. And you can see it roughly picks up the block pattern, right? So the first kind of 5 are somewhat lower, and the second 5 are somewhat higher, right? So it's not as pretty as the truth was, but it's somewhat discernible that there are 2 different kind of means here. The second right singular vector is on the right-hand panel here, and you can see that it's a little bit harder to see, but it does try to pick up the alternating mean pattern, right? It's not as obvious as it was when we were plotting the truth, of course, but you can see that every other point is either higher or lower. Now, of course, since we know what the truth is, it's a little bit easier to kind of talk about this. But in general, the two you can see that the 2 patterns are roughly confounded with each other because it's a little bit hard to separate the 2 patterns apart. So even though they're clearly we know that the truth is 2 separate patterns. The first and the second right singular vectors are also known as the principal components. They kind of mix the 2 patterns together. So each of them has a block pattern, and each of them has a kind of alternating pattern. And so, unfortunately, just like with most real data, the truth is a little bit hard to discern than if you'd known it in advance. Now, if we look at the variance explained in this problem, you can see that on the right-hand panel, which is the percent of the variance explained, that the first component explains over 50% of the variation, the total variation in the data set. And that's basically because the shift pattern, with the first 5 columns, the second 5 columns, is so strong, it represents a large amount of variation in the data set. And so if you capture that shift pattern, you kind of capture a lot of that variation. You can see the second component only captures about 18% or so of the variation, and it kind of trails off from there. And so that kind of tells you roughly how many components are in this data set. But that alternating pattern, which is kind of every other column, is a little bit harder to pick up, as you can see.